So at the moment, we've got AI. AI is a massive sector. Within AI, which is a part of computer science, you've got also machine learning. So you've got machine learning, which is a part of AI, so it's a subset of AI. Part of that, you've got supervised learning. You've got reinforced learning. You've got unsupervised learning. And I'm going to introduce you to this concept of, let's use a different color, deep learning. Now, this is a subset of machine learning as well, but it's slightly different to the others. So let's have a look at some fundamental differences between the two. When we talk about machine learning, we talk about data which has been labeled, like this is an apple. And we have humans who oversee the training. In unsupervised learning, we have an apple again. This is a really badly drawn apple. But we hope that the computer, or the machine shall we say, is able to, once we give the data, discover patterns and then group them. So all of these, what you've given me are apples. So that's an apple, that's an apple, that's also an apple. Actually, we kind of look like cherries, but never mind. And it's able to say, okay, this group, that's a banana, that's a banana, that's a banana with a bit of black on it because it's rotten. So that is using supervised and unsupervised learning. We've looked at that already, using labeled data or unlabeled data. With labeled data, it's meant to give a prediction. With unsupervised learning, it's meant to classify into groups. With supervised learning, it relies on, as I said, the labels to make those predictions. With supervised learning, it requires a lot of human interaction because we've got to do the labeling, we've got to do the correcting, etc. With unsupervised learning, the amount of human interaction goes right down. It's not much at all. So humans aren't really involved too much with that. It's lower in terms of that. You'll notice that I'm not talking about deep learning yet, and there'll be a reason. So with supervised learning, it's really simple models which are used. So it's nothing too complicated. So it's a simple model process. So whilst you've got lots of human interaction, it's using labeled data, it's used to predict, so to speak. It's very simple in terms of its model. Again, with unsupervised, the model is more complex than using its counterpart of supervised. So it's more complex. So that means it's being coded. The way it works is more challenging to understand, the code, etc. It's harder to maintain. But we're going to see that in comparison to deep learning, it's still pretty basic. In terms of how did we get there? So we see a result. Okay, this is an apple. And we say, yay, tick. With supervised learning, it's quite clear on how the computer made that decision. How the system said, okay, you've given me a picture of an apple. This is an apple. You give me a picture of a banana, this is a banana. It's easy to see how it came to that conclusion. It's based on our labels. With unsupervised learning, it is less transparent. So it's less clear to how it's done that. Because it looks at patterns, in essence. It's hard for us to work out, okay, but what made you say this was an apple? What made you say this was not an apple? So where does deep learning come into this? Well, let's have a look at deep learning in itself. So deep learning is made up of neural networks. So everything I'm going to highlight right now is a neural network. This neural network is basically mimicking how our brain works. How our brain works is that we've got neurons. Every time we create something, or every time let's do this as a scenario. This is a person. A person sees, I don't know, or let's do smell, that'll be even better. Smells popcorn. This could be my popcorn. For the first time. It's going to create in the person's brain, this is the neurons, a connection. The connection is the movie theatre to popcorn smell. And it's going to make it quite strong because it's a brand new connection. The more times they go to the cinema, the more stronger this connection becomes between these two neurons. Let me make the neurons a different colour. Now let's imagine that this person goes to a festival, or a fair, for the first time. And we also walk by a popcorn stand. What's going to happen is this. They see that the smell, it then brings back their memories of where they've had that smell before. Popcorn associated with movie theatres. Hang on a minute, this smells like a movie theatre, a cinema. Then what happens is it creates a brand new connection. This connection will be a new neuron, and it'll be connected with the cinema, movie theatre, and the popcorn by association. The more experiences this person has, the stronger. So the more, let's say, theme parks and things they go to, the stronger the connection gets, and it might even weaken the cinema connection slightly. So as we learn, neurons, which we might have somewhere else, create new connections. So we had, let's take that theme park connection. Let's imagine that we've been to many theme parks, but we've never walked by a popcorn stand before at a theme park. So we do have theme park neurons about theme parks. But when we get to this one theme park and we walk by a popcorn stand, it creates that connection with the movie theatre. So these neurons are created and they form connections in our brain. When it comes to deep learning, it works exactly the same way. Now, it involves statistical relationships between these nodes. So these are nodes, node, neurons, nodes, same thing in this concept. So nodes, and it looks at the relationships between these different nodes. And these different nodes and the relationship is done based on stats. That's how these connections are made. Like in our brain, it's done via stats, it's done via probability, it's done by experience, it's done by the amount of times I've experienced something, the stronger that connection, so the higher the stat is going to be, the stronger that relationship. Now, what we're going to look at in a second is how this actually works. So let's imagine that we've got 3 people. Person 1, person 2, and person 3. And each person was told to draw an apple. So if I was to do this, well, let's do cherry, because these actually look more like cherries than apples. So the composition was, these kids were told to draw a cherry. A teacher comes in to the room and is told that these kids have drawn a fruit, but not what a fruit is. Guess the fruit. oh, it's a cherry. This is also a cherry, whilst you're missing a little thing here. It's still recognized as a cherry. I'm not sure if you even need that, but whatever. This is also a cherry, but a little stalk thing's going the other way. But they're all drawn differently. Humans are able to accomplish that. But what about computers? How can computers actually operate with differentiation between the same task, i.e. draw a cherry, but they're done in different ways? So what we have here is basically this schema of how deep learning works. I want you to picture right now, these are our neurons in our brain. But you'll notice that these neurons are different colors. So you've got this orange here, you've got this blue here, and you've got this lighter blue over here. But we've also got these, which are, I'm going to put these as neurons as well. Each one of these represents an output. So I'm going to write the word output here. So it's either going to be an apple, a cherry, an orange, a lemon, or a pear. This is our output layer. What we're feeding into this neural network, so I'm just going to put neural network here, and a neural network is a part of deep learning, is this image. This image is of a cherry. It's by 2828 pixels, which if we multiply them together, it's 784 pixels. This is what we're feeding into the system. What we have here are neurons. With our neurons, though, they're put into different layers. So this would be our input layer. I'm going to put input layer down here. So these orange represent our input layer. The red here represents our output layer. The blues, and I'm going to put like this on this side and this here, is what's known as the hidden layer. So we've got our neurons, we've got our image, we've got our input layer, we've got our hidden layers, and we've got our output layer. These neurons are connected, so our input layer is connected to the hidden layer via these lines. These lines represent what is known as channels. So a black line is known as a channel. These channels, let me just continue this for a second, it's going to get a little bit messy. Will have a numerical number on it. So let's imagine this was 0.1. For x2 to this, it'll be 0.8. Let's do 0.6, 0.3, 0.5, 0.9, 0.7, 0.1, 0.9, 0.2. So these are weightings, which I'm drawing out right now. Now, each neuron, which is within our hidden layer, has a unique number associated with it. This would be known as a bias.
Have a unique number associated with it called bias. This bias is added to the weighted sum of inputs reaching the neuron, which is then applied to a function known as the activation function. The result of the activation function determines if the neuron gets activated. Every activated neuron passes on information to the following layers. This continues up till the second last layer. The one neuron activated in the output.
Okay, so what we have here is an overview now of how this works. We feed in the cherry image. The cherry image is then going to go down the input layer, which is this. using some sort of algorithm, what will happen is it'll go through the biases, it'll take into account the input, the weight, and the bias, and what will happen is certain nodes will become activated because of it, because of that input, based on the highest weight or the best weighting from the formula. So think of it like this. This is a cherry coming in. This system has to cope with every single possible fruit that it could be. It could be an apple, it could be a cherry, it could be an orange, a lemon, pear. These hidden layers are responsible for using these weightings, using the input, and using their own biases to try and filter out different features of the cherry and eliminate what it definitely won't be during this process of elimination. So you'll see that certain biases will start activating certain nodes. So you'll see that B1, B2, 4, 5, 6, 7, and 9 on this layer. So this basically filters out, it crosses out this one, it crosses out this one, and it crosses out this one. So based on the formulas of what's been generated, based on the image being inputted in the first place, these biases are meant to, each layer of these biases, get it closer to the exact output what it needs to be. So as we'll see this process again happening, it's going to be fed in through the input layer, goes through the biases, and then it goes to this layer. This layer eliminates this one, this one, this one, and this one, and eventually it will get to one of the outputs, and one of the outputs would be the correct one, hopefully. So it would recognize it's a cherry through going through this process. What can happen then? Let's imagine though it said it wasn't a cherry, let's say it was an apple. Our system isn't working the way we want it to work, and that could be because certain nodes or biases are wrong. So we can actually go back and make modifications to our model. So we can say 0.4 for this, for example. That means potentially that this one doesn't get activated either. It's this node which is making it seem like it could be an apple. And let's imagine it was this node as well, which makes it more like an apple. So by changing our calculations, our weightings, our biases, etc., we can actually eliminate certain nodes from operating, which means that hopefully our output becomes more accurate. So by us eliminating certain or changing certain weightings, we're basically saying, yo, this isn't an apple. You're thinking it's an apple because of this, but actually it's not. Look at the size of it. So we change the weighting where it talks about size, and hopefully the output's going to be more accurate. So what do you need to take away from this so far? You need to take away that deep learning works via, it takes in an input, it goes into the input layer. The input layer has several nodes, well actually lots and lots of nodes. Each input layer is connected to the hidden layer through weighted channels. These weighted channels can be altered, they can be modified to help train the model. It then goes in the hidden layer. The hidden layer is made up of biases. It's a sequential system. These biases, when it goes through these, will activate the next layer to the next layer. So there could be, theoretically, another. So this could be B1, B2, B3. So each layer, you'll notice, is getting smaller and smaller and smaller in terms of nodes until we get to a final output. So only the biases which the system believes will help us come to our final conclusion will get activated. Those which have nothing to do with our final solution won't be activated, like B3 in this situation, and this one down here, and on this one all of these with X's on it. So eventually it just correctly gives us cherry. So what do we want from this? We feed in this picture, by the end of it, it should be able to tell us it's a human. We're going to build a neural network which hopefully would be able to do that. So the first thing we need to do is feed in the picture. This is a picture of a person. Copyright purposes, I found this on the internet. I can't remember the source, but never mind. It then needs to go to the input layer. The input layer contains, in this case, like 700,000 different nodes. These nodes would represent each one a different pixel. That pixel will have a number between 0 to 1. So it could be like 0.8. This next one could be 1. The next one could be 0.2. And it'll be based upon the color itself, the lightness. So let's do 0.9, blah, 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 all the way to 700,000. So that would be our input layer. So what happens next is we have our next layers, which is the hidden layers. So I'm going to do hidden here. And let's say that those pixels from the input layer pass the information to this hidden layer here. Let's say this hidden layer here has 1.0, and its job, this part of the hidden layer, is responsible because it's been trained to go to this picture and make an identification. And let's imagine its job is to go to the picture, to the center, to find the nose and look at the curve at the top of the nose. Its job is just to take care about this part of the nose. It doesn't care about the rest of this face. It's just the tip part of the nose, just that. And what will happen is it will take the input values, it'll perform a mathematical calculation and come up with a number, let's say 0.8 in here in this hidden layer, node 1. And this 0.8 is basically like a guess, saying the likelihood that this is a human top part of a nose. So 0.8 is quite high. So it's basically saying, I'm taking a guess so far that this is a part of a human nose, the top part. We then have other neurons in the hidden layer, which are responsible for other parts of the image. So let's say this purple is responsible for other curvatures, like the curving of an eye. Or the top part of an eye, so let's move it up slightly. Whilst you might have others, which is responsible for like the amount of shine. I'm not sure if that's a thing. Reflection, shine, yeah, we can call it that, of the picture to show you that there's skin there as well. So all of these are obviously still connected to neurons from the input layer as well, with their own weightings, which will be a part of this calculation as well. So the hidden layer, remember, is made up of actually multiple layers. So let's do the next layers. So let's put another neuron here. As we progress going this way, the job of these neurons become more and more complicated. So to start with, this 0.8 here was responsible for seeing the curvature of the nose, just the top part of the nose. But let's imagine that we have another neuron here, and that is responsible for, actually we have that in red, the bottom part of the nose. So this bit is the bottom part. Let's imagine that was the bottom part of the nose. And that was at 0.8 as well. What would happen is the results from all the neurons from input there will be passed into this neuron. This neuron is responsible for looking at the whole nose as a whole. So it will take into account, let's do this in a different color in fact. Let's do this in purple. It'll basically look at all of that. So let's imagine that we would have had another neuron here, which is responsible for the top of the nose, then another one for the middle. Everything gets fed into this neuron, which is responsible for the whole nose. This neuron, in its calculations, would ignore, even though they'll be passed in. So let's take into account again. I hate changing the color, so I'm just going to stick to red here. This neuron, remember, was the skin. This one was the top of the eye. So let's imagine that the top of the eye was 0.6. It would ignore that 0.6 because it doesn't care about the top of the eye to work out the nose. This is just the nose. So it'll take into account all of these to give it a calculation, like the 0.8, the 0.8. Let's imagine this was the middle of the nose. Actually, this was the top of the nose. Let's say this is 0.7. It'll come up with a calculation and give a result here. And like before, different neurons get activated based on probability. So 0.8 is high, so that'll be activated and passed on. Anything which is low, let's imagine there's nothing really low about this. Well, actually, it'll be like this sort of space here. It'll look at this sort of space and then ignore it. So any new input neurons which we're looking at this, it'll say, is this like the neck? Is this like the part of the chin? If it doesn't meet any of those criteria, it just won't activate when it comes to the next layer. So nose will be activated. It'll then pass it on to the next thing. There'll be another neuron here in the hidden layer, which will be looking at the whole cheek. This one will be looking at the whole eye. And when it gets passed on to the next layer, it'll look at piecing things together. It'll look at the spaces between the different components. Eventually, in this situation, it's either going to be a human or not a human. So it'll light up the one with the highest probability. This whole process is called forward propagation, which is basically, sorry, that's meant to be an A. Propagation. The process of taking this input, going through these different layers, extracting different information of these different layers, through the biases of the hidden layers and the weighting, to finally get to a output which is desired. That is forward propagation. We've also, in this video, hinted at this process of backwards propagation. So let's explore that in a little bit more detail. So backwards propagation is where things don't go to plan. We put this image in, but it tells us it's not a human instead of it being a human. Oh no, what do we do? Well, we've got to work our way backwards to try and find out where this issue is and train the system better so that it doesn't make the same mistakes again. That would be backwards propagation. What we're going to be doing is error correction. So backwards propagation is all about error prevention by training our model, by adjusting the weights to working out where things are going wrong to reduce the probability of an error. So it doesn't eliminate, it reduces the probability of that error. So this is actually known as gradient descent. This whole process of us performing forward propagation to then perform backwards propagation to make improvements in terms of predictability, accuracy of machine, it's a gradual approach. It doesn't mean that we're going to turn it from not working to perfect straight away. So it's a gradient descent in respect, thus finding the most optimum pathway through these biases and weights to get to the outcome we desire. Remember, this isn't about perfection. This is about the optimum or the optimal. It's never going to be perfect. Take ChatGPT as a great example of that. It's still littered with mistakes and issues. But through training, through backwards propagation, through weights being changed, through biases being changed, accuracy does improve. So let's imagine right now that it said it wasn't a human in itself using backwards propagation. What we'll do is we will first of all calculate what is known as the loss cost, or in geeky terms, loss calculation. Okay, so let's imagine right now that for our loss calculation, remember computer deals in binary, so human, we want it to be closer to a 1, not human, closer to a 0. We feed this photo through forward propagation, so it goes through the input layer, then the hidden layers, etc. And it comes out and it says 0.4 for this being a human. Obviously, that's closer to 0, so it's going to say it's not a human as an output. We know this is wrong. We know that actually it's definitely a human. So what we're going to say is, no, we don't agree with that. We don't agree with your 0.4. So we're going to change this to be 0.6 using a calculation. So we're going to decide to change it to 0.6 using loss calculation. Loss calculation takes what it should be, the end result, and finds the difference, which would be 0.6. So it should be a 1 for human. We got given 0.4, that it's not really a human. 0.6 is is our outcome. So what we'll say is, let's deal with this as 0.6, make changes going backwards to make sure that this happens. So what will happen is through backwards propagation, it will go backwards and it will change the weightings, and it will also change the biases on the different neurons on the different hidden layers. So you've got hidden layer, hidden layer, hidden layer. So it's kind of like changing a knob on like an oven, so to speak. It'll just change it slightly this way, or alter it, it'll alter it slightly this way, it'll alter it slightly this way. And it'll find, so let's imagine that it was the mouth and cheeks and ears which were really low, so 0.2 for cheeks, 0.1 for ears. It would also change those to go up slightly as well, and overall it'll start training our model to make it 0.6. So hopefully new photos which come in, it takes into account these new weightings and these new biases, and it's going to be an iterative process, because let's imagine that we make these changes, it sends it through 0.6, human, 1, great, but then we put a new photo in, and for this new photo they're slightly different in terms of appearance. We're going to have to go forwards propagation and backwards propagation again and again and again based on the data. And also 0.6 isn't going to be high enough, so we might then say, okay, once we've done 0.6 and it's recognizing human, how can we make it 0.8? So we go backwards propagation and then we go forwards propagation. So this whole process is iterative. We basically, every time we make a change, we hope it's going to be more accurate in the outcome the next time. That is backwards propagation. Forward propagation is needed to begin with.